everyone, this is your instructor Munira Topia. Welcome to the video lecture series of algorithms. In today's video, we are going to cover asymptotic notation, big omega, big O and big theta. Now, what is the asymptotic notation and why would we require them in our algorithm? In order to solve a single problem, there do exist various algorithms to solve a single same problem. To choose the best algorithm among them, we need to check their efficiency and we have to compare the efficiency of each. Now, efficiency of algorithm is calculated in terms of time and in terms of space. But right now, we are actually discussing time complexity. So time complexity is represented by asymptotic notation. Asymptotic notation gives us fastest possible, slowest possible and average time complexity of any algorithm. So we use various notation inside asymptotic notation like big O, big omega and big theta. So let us look into them in detail. Starting with big omega notation. Big omega notation is used to represent lower bound of algorithm. It is actually denoting shortest amount of time which is taken by algorithm to complete. Now, what is the formal definition or mathematical representation of big omega? Let f of n and g of n are two non-negative functions. F of n is complexity of first algorithm and g of n is this lower bound. Now, we say f of n is in big omega of g of n only if f of n is greater than or equals to c into g of n, where values of n are greater than n naught. Now, what does we mean by this mathematical definition? Let us go back to first line of our definition. Let f of n and g of n are two non-negative functions. Since these are non-negative functions, we are going to plot them in our quadrant 1 where x and y values are positive. Our x value represents n, which is nothing but size of input, and our y-axis is representing time, which is nothing but running time of an algorithm. And we will plot a function f of n. Let me plot function f of n. Say this is a function f of n which is represented for some input how much time it takes. And there is another function that is c into g of n. Now as you see, f of n is always greater than cg of n. Not every time but after some time. So that particular case is, or that particular set of input is n naught. So after every input n naught up to n, every value of n, my f of n is always greater than cg of n, where n is the input size, c is simply a constant which is non-negative, and n naught is always greater than or equals to 0. It should be a non-negative. That means input cannot be negative. Once again, let me revise the definition. Since f of n and g of n are two non-negative functions, that's why we are going to plot them in a first quadrant. Now let there is a function f of n that is represented this way, and there is another function g of c into g of n that is represented another way. So as you see, at first time, sometime f of n is greater than g of n and sometimes cg of n is greater than f of n. But after some point of time, my f of n is always greater than or equals to c into g of n. So that particular input point is called as n naught. So what are the variations towards the left of that side? It doesn't matter. The only matters for the larger size of input how my f of n is greater than cg of n. So big omega, we will take one example to understand. Let f of n is 2n square plus 5, that is one function, and g of n is equals to n, that is another function. Can I say f of n is in omega of g of n? So, is it a correct representation? To prove that f of n is in omega of g of n, we have to find a constant such that f of n is greater than or equals to same to g of n. This is by the definition of big omega for all values of n greater than n. So, in place of f of n, let me substitute value of f of n that is given in question. That is 2n square plus 5 should be greater than or equals to c into n. This n comes from input that is given as g of n is equals to n for all n value greater than n naught. Now, what we have to take is we have to decide a constant. We want our right hand side term to be lesser than left hand side term. That's why we will choose any constant which is lesser than left hand side term. So we will choose constant as 1 and we will select values of n and keep on putting and see that this relation does exist or not. So f of n equal to 2n square plus 5 and 1 into g of n. This constant 1 we have taken or we have decided by ourselves. So 1 into g of n is equals to n. Now we will put n's value here. So 2 into 1 square plus 5 is my f of n, whereas 1 into 1 that is equals to g of n. So f of n's value is 7 and g of n value is 1. We say that f of n is in greater than or equals to c into g of n when n is equals to 1 and c is equal to 1. Now, when n is equals to 2, what will happen? F of n equal to 2n square plus 5, that is 2 into 2 square plus 5, that is equals to 30. While c into g of n, that is 1 into g of n, is equals to n, which is equals to 2. Now 13 is still greater than or equals to 2. So we say still my f of n is greater than cg of n when n is equals to 2. For all values which are greater than or equals to 1, my f of n is always greater than cg of n, or f of n is equals to omega of g of n, where c is equals to 1 and for all inputs greater than or equals to 1. So this way we can see or we can find out upper bound. Now we will see big O notation. Big O notation is used to represent upper bound of an algorithm. It is an algorithm's longest amount of time that is taken to complete. Now, what is a mathematical representation of big O? Let f of n and g of n are two non-negative functions. Again, those functions are same. That's why we represent them on a first quadrant. Then we say f of n is in big O of g of n if f of n is less than or equals to cg of n. Remember this sign, less than or equals to, for all values of n greater than n naught. So what it means to say is that if there is a function that is f of n and there is another function that is cg of n, it is always that my f of n is lesser than or equals to cg of n after some moment or amount of input. So towards the left of n naught doesn't matter who is greater and who is smaller, but towards the right of n naught for all values of n which is greater than n naught, for every input my f of n is always less than cg of n, and where c is non-negative constant and input is always positive. Let us take an example and see how big O works. So here f of n is given as 2n plus 2, while g of n is given as n squared. Can I say f of n is equals to or is in big O of g of n? To prove that big f of n is equals to big O of g of n, we have to find a constant c such that our condition f of n less than or equals to cg of n is satisfied for all values of n greater than n naught. That is, in place of f of n, we are substituting f of n's value. In place of g of n, we are substituting given value. So it becomes 2n plus 2 is less than or equals to c into n squared for all n greater than n. So let us try to select value of c. Now observe your left hand side. It is having the term of n with the highest power is 1. So degree of polynomial on the left hand side is 1. While right hand side we are having n square term. Degree of polynomial is having degree 2. So obviously right hand side is directly greater than left hand side, but still we want to choose some constant. So let us take or choose constant as 1. Now we will keep or find the values of n, keep on substituting in this equation and see that and show that that condition still satisfied. So f of n equal to 2n plus 2 and 1 into g of n is nothing but 1 into n square. If n is 1 substituted, it becomes 2 into 1 plus 2, that is equals to 4. And here value of 1 square, that is 1. So 4 is greater than Cg of n. This doesn't satisfy our big O condition. Big O says f of n should be less than or equals to Cg of n. So for n equals to 1, our condition doesn't fulfill. So let us try with n is equals to 2. For n is equals to 2, f of n equals to 2n plus 2. That is 2 into 2 plus 2, that is 4 plus 2 equals to 6. And 1 into g of n, that is n square, that is 2 square, which is equals to 4. 6 is still greater than or equals to Cg of n. But big O's definition says that f of n should be lesser than or equals to Cg of n. So for n equals to 2, our input doesn't satisfy the condition. Let us take for n is equals to 3. For n is equals to 3, 2 into n plus 2, that becomes 2 into 3 plus 2, which is equals to 8. And c into g of n, that is 1 into n square, that is equals to 3 square, which is turns out to be 9. Here 8 is lesser than or equals to 9. So we here say that my f of n is lesser than or equals to Cg of n when n is equals to 3. We are going to process in the same manner. F of n is 2n plus 2, that is 2 into 4 plus 2, that is equals to 10. And Cg of n, that is equals to 1 into n square, that is equals to 4 square, which is equals to 16. That is, again my 10 is less than or equals to 16. So we say that f of n is less than or equals to Cg of n when n equals to 4. Hence we can calculate for the larger values of n, and we can conclude that for all values of n that are greater than or equals to 3, my f of n is in big O of g of n, where constant we have selected is 1. Or we can say that 2n plus 2 is equals to big O of n square. What is big theta notation? Big theta notation is used to represent upper bound as well as lower bound. While your big omega is representing only lower bound, your big O operation only representing upper bound, your big theta representation is used for both upper and lower bound, which is also called as tightest bound of an algorithm. Let us define them mathematically. Again, I have two functions f of n and g of n, which are non-negative. Hence, we are representing them on a positive first quadrant of axis. So x represent my input, that is an n, and y state axis represent running time of an algorithm. If there is a function f of n, then there is another function c1 into g of n, which is always smaller than it. And there is another function c2g of n, which is always greater than f of n. So it is written it as f of n is in theta of g of n only when c1 g of n is lesser than f of n and f of n is lesser than c2 g of n. So this relationship should be maintained. If this relationship be maintained for all values of n naught, n greater than n naught, then we say that f of n is in big theta of n. Take an example of big theta. My f of n is 2n plus 8, while g of n is equals to n. Can I say f of n is equals to theta of g of n? Prove that we have to show that f of n is in theta of g of n. We find a constant such that condition c1 g of n is less than or equals to f of n is less than or equals to c2 g of n for all n greater than n naught is satisfied. How these constants c1 and c2 has to be chosen? So first we will compare c1 into n and its right hand side, that is our middle term, 2n plus 8. If we compare left hand side term with middle term, both functions are having same polynomial degree. Polynomial degree of c1 into n is 1 and 2n plus 8 is also having polynomial degree as 1. So polynomial degree of both functions are 1, same, that is 1. So we have to choose constant in a such a way so that makes my left hand side term automatically greater. So on the middle term n is having constant 2. So we will select n's constant on left hand side is any value which is lesser than or equals to 1. But by definition constant cannot be 0 or negative. It has to be positive. So only value that is left for c1 is equals to 1. So we will select our constant c1 is equals to value 1. Now coming over constant value 2, that is c2. If we compare middle term with our right hand side term, so degree of polynomial is again same on middle term and right hand side term. So we have to only make use of constant. The constant on the left hand side is 2. So we can choose any constant which is greater than 2 on our right hand side term. So I can choose constant as 3, 4, 5. That will also satisfy our condition. But for better results and to minimize your calculation, one tip you should remember is that you use sum of constant of all the terms of middle term. So constants of middle term are 2 and 8. Sum them up, whatever value you get, you have to set that value as C2. So we will choose C2's value all greater than or equals to 10. So we take C1 is less than or equals to 1, which is ultimately 1, and C2's value which is greater than or equals to 10. Let us take 10 for let us test this condition for n equals to 1. So my f of n is 2n plus 8. If I substitute 1 there, it becomes 2 into 1 plus 8. So answer is 10. While c1 into g of n, that is 1 into n, that is equals to 1 into 1, the result is 1. While calculating c2g of n, so c2g of n is nothing but 10 into g of n. I can choose any value which is greater than or equals to 2, but for removing or to minimize the calculation, I have chosen 10. So 10 into n is equals to 10 into 1, which is equals to 10. Now, in this case, 10, 1 is less than or equals to 10, and 10 is also less than or equals to 10. So we say that we will c1 g of n is less than or equals to f of n is less than or equals to c2 g of n for value of n equals to 1. Now, does this condition also satisfy for n equals to 2? Let us check it out. Again, we will not change our constant. C1 is still 1 and C2 is still 1, 0. That is 10. So f of n is 2n plus 8. That is equals to 2 into 2 plus 8, which is equals to 12. C1 g of n is equals to 1 into n. That is 1 into 2, which is equals to 2. C2 g of n is equals to 10 into n, which is equals to 10 into 2, which is equals to 20. Now you see that 2 is less than or equals to 12, 12 is less than or equals to 20. The value of C of g of n, C1 into g of n is less than or equals to f of n is less than or equals to C2 g of n, where n equals to 2. Hence we are concluding for all values of n that are greater than or equals to 1, where C1 is selected as 1, C2 is selected greater than or equals to 10, f of n is in theta of g of n, or 2n plus 8 is equals to theta of n. At the end of this lecture, you should know what is asymptotic notation and why we are using asymptotic notation. What is big omega notation? What is big theta? And what is big O notation? Thank you everyone for watching this video. This is your instructor, Munira Topia, signing off.